Hello everybody, my name is David Pitones. I'm going to be solving Griffiths problem 2.48, which asks us to do the following. An inverted hemispherical bowl of radius r carries a uniform charge surface density of sigma, and to find the potential difference between the north pole and the center. So the first thing I'm going to do is I'm going to draw our bowl. So here we have our center point, and right here we're going to have our north pole. And so the equation we're going to be using to solve this problem is the electric potential is equal to 1 over 4 pi epsilon naught with the integral of the differential charge over sigma r, where sigma r is equal to the field point minus the source point. Let me actually fix this real quick. The field point shouldn't have a comma. It should have nothing. The source point should have a comma. And so we have this. First things first, we're going to solve for our potential at the center over here. And so our equation should look like the following. Notice that I'm writing sigma dA instead of sigma dq. The reason for that is because since we're dealing with a bowl, this is just infinitely thin, and it's like half of a spherical shell. And so now we have this. The goal for this part is to solve what script r is. Well, if we're trying to take the source point, we know that the source point is just this part right here. And so we know that since we're dealing with the center as our electric potential, it's just from here to here, but that's just the center of a sphere to the edge, which is just the radius, big R. So for this, we can say that, or for this part, we can say that script r is just equal to the radius. And with that, we know that the equation is just going to boil down to this. Now we gotta wonder what dA is, but since we're dealing with a spherical geometry, yeah, it's just gonna be the double derivative, or I mean double integral of r squared sine theta d theta d phi. Since we're dealing with a constant radius, then this little r just becomes big R. And since we're dealing with half of a spherical shell, then we know that, that theta is going to go from 0 to pi over 2, while phi is still doing a whole rotation. And so it's still going to go from 0 to 2 pi. So if we rewrite this, we're still going to have these terms, and then we could take these terms right here out of the integral, and we should have the following. So we should have sigma r squared over 4 pi epsilon naught, and yeah, we should have an r right here. And so we're going to cancel this out right here and this out right here, and so we just have integral of this term inside, so d theta d phi. And we know that since there's no d phi term, d phi just equals this, which is 2 pi phi from 0. So d phi, this gives us phi evaluated from 0 to 2 pi, which is just equal to 2 pi, and we can actually knock this out of the integral as well. So what we have now is sigma r over, oh, sorry if I didn't see that. We have sigma r over 4 pi epsilon naught times 2 pi. We have the integral of theta from 0 to pi over 2 for sine theta d theta. We know that the integral of sine theta is just equal to minus cosine theta. So we're evaluating it from pi over 2 as upper bound, at 0 from the lower bound. We know that cosine theta evaluated at pi over 2 is just equal to 0, and so minus from here. So cosine theta evaluated at 0 is just equal to 1, so we just get 1. So that tells us that our electric potential at the center is just equal to following sigma times capital R over 4 pi epsilon naught. Now we can box this because it's going to be one part of our solution. Now our next thing to do is to solve for the potential at this north pole right here. So what we're going to have to do is we're going to have to find the script R. That's going to be the biggest problem, but for now I'm going to write out our equation, which is pretty similar to the equation we have like right here, but the script R is going to be different. 1 over 4 pi epsilon naught with the integral of sigma dA over script R. And so for script R, if you see this, we know that the source point is going to be the same as the previous. It's just from the origin, but this time it's going to the source point, and from the source point we have to go to the north pole. We know that the field point is going from the center or the origin to here. We also know that this, and this right here is going to be our script R. Since we're trying to find it for like a general case where the source point can be anywhere in the sphere, right? We have to use a very general equation to find what script R is. And that equation is going to be called the law of cosines. So normally when you're writing out the law of cosines, it's the leg you're trying to find, which is right here, and the length of the other two legs, which is just this one right here and this one right here. They're both R because you're going from the center to the edge of a sphere, which is just a radius. And so then it's subtracted by this term right here and cosine gamma. For this, we can rewrite it, or for our question, we can rewrite it as the following. Script R is equal to R squared plus R squared minus 2R squared cosine theta. The reason why we're going to write it as theta is because by using theta, that means we can encapsulate all the source points from here, or from here, or from here. And so that's why we're going to be calling this cosine theta. And so if we put this back into our original equation, we get the following. Let me write this out. So we have, actually, before I write this out, I think it'd be very useful for us if I were to simplify it. So we get 2R squared minus 2R squared cosine theta. And if you notice, these terms are alike, so we can factor that out with the 2 being in the square root, the R just being regular R. We're just left with 1 cosine theta inside of the square root. And so if we have it here, let me actually erase some of this square root so I can write our terms properly. So we have square root 2R square root 1 minus cosine theta. And so now we have this. Since these three terms are constant, we could just rip them out of the integral. So we have 1 over 4 pi epsilon naught times sigma square root 2 over, sigma over square root 2 times R. And so what our integral is going to be is the integral of dA. And we know that since we're still dealing with a spherical geometry, our dA term is going to just be equal to this following. Oh wait, I should also write the law of cosine, but since there's a little bit of space error, I'm going to just write it over here. So what we're going to have is a double integral going for theta from 0 to pi over 2. This is going to be the bounds are going to be really the same as we did for the center, because it's like the same geometry and everything. And then for phi, we're going to go all the way up to 2 pi. And so we should have sine of theta over square root of 1 minus cosine theta. d theta, d phi. And so if you look at it, it should be pretty blatant that we're gonna have to do a u substitution, with u being equal to 1 minus cosine theta and du equals sine theta d theta. And so if we do that, what we're left with is the following. Let me shift the camera a little. What we're left with is the following integral. Actually, before I do the u substitution, notice that there's no d phi term, and so d phi evaluated, or the integral of d phi at this, we're just going to get this little integral, which you can do separately. And so we just have phi evaluated at 2 pi, or from 0 to 2 pi, and that's just equal to 2 pi. So we're going to be able to actually rip this right here, and drag it all the way over here, which I'll do later. But for now, I want to solve this integral for theta. And so what we're going to have is their integral, but remember that we were doing a u sub. So this term this term right here just turns into a du. So we have du over square root of u, because this term right here is just u. And so we have this right here. And so if we evaluate it, we should just get, well, let me just do the power rule, just so I make sure I'm right. Half minus 1/2, because this is like equivalent to 1/2 right here. This is equivalent to each other. So minus 1/2 plus 1, u to the power of 1/2 plus 1. So then we get u 2u 1/2. And so now we should be able to evaluate this. Well, after we plug in back what u is. So we know that what we're going to have is 1 minus cosine theta evaluated at pi over 2, or the upper bound's going to be pi over 2 and the lower bound's going to be 0. And so we know that pi over 2, or cosine theta evaluated at pi over 2 is 0, which gives us 2 times 1. And then cosine theta evaluated at 0 is just 1. So 1 minus 1 is 0, so minus 0. So this is what we're going to get for this integral. So now if we plug everything together, this is the following equation we should get for the electric potential at the North Pole. So we have this term right here. Don't forget the 2 pi we did earlier. 2 pi times 2. And so it is looking pretty good, because these 2's cancel out this 4, and these pi's cancel each other out. And so the electric potential at the North Pole is just equal to, actually, I realized something. So over here, there should have been big R squared. Now the reason is, as I mentioned earlier, our Jacobian is r squared sine theta. I forgot to write it, the r squared term. But there should be an r squared term, and this r squared term should carry over, or it should be knocked out of the integral. This should be over here as well. And so now we're going to be doing some simplification. This r term should be like right here, and we could just cancel out the square, and we can cancel out the r on the bottom. And so now we're able to write the actual electric potential at the North Pole, which is r times sigma over square root of 2 epsilon naught. And so remember that the question is asking us to find the potential difference between the electric potential at the North Pole and the center. And so with this piece of room I have, I'm going to do that. So we have electric potential at the North Pole, electric potential at the center, and so we have sigma r over square root of 2 epsilon naught minus sigma r over where is it? Well, it's gonna be 2 epsilon naught. Actually, there's something wrong with this right here. Let me double check my work real quick. well. There's 2 pi right here. Actually, this isn't the electric potential. The electric potential should be the following. Electric potential at the center is sigma r over 2 epsilon naught. And the reason for this is because we take out this term right here, this term's right here, and then when we're doing the integral, there's an r squared. The r's cancel out, so there should be an r on top. Then we get 2 pi, and so this 2 pi term right here, let me just explicitly write this out, right? My apologies again for doing this mistake. So we have a 2 pi on the top, 4 pi epsilon naught. So the pi cancels, the 2 cancels, and then the 4 gets reduced to 2, and that's how we get our electric potential at the center. Now that I've remedied that issue, we have this right here, going back to our final solution. So you can see that these 3 terms are equivalent, so we're going to just be able to factor that out. So we should get sigma r over epsilon naught, and we have square root of 2 minus 1 over 2, and Griffiths puts his answer with a 2 on the bottom right here, so we're going to factor out 1/2, and to do that, that's just equivalent to saying this right here. Because if you want to factor out 2, you're going to have to put a 2 on top. And so we know that 2 over 2 is just equal to 1. And then 2 over square root of 2 is just square root of 2. And so our final answer for the potential difference, for our potential difference minus the potential, or the potential difference at the North Pole minus the potential difference at the center, is just going to be equal to sigma r over 2 epsilon naught with the parentheses of square root 2 minus 1. And this right here is our final answer for Griffiths problem 2.48. And this was done by David Pitones. Thank you for watching.